Greetings to everyone. I'm Tommaso Zana, postdoc at Scuola Normale Superiore in Pisa. And first of all, I would like to thank the organizers for the opportunity to share with you the results of my latest work on the effect of AGN feedback onto the satellite galaxies at high redshift. According to theoretical models, the efficient gas inflow necessary for the growth of the most massive black holes powering the brightest quasars is likely to be satisfied within the most massive dark matter halo. But unfortunately, observations have not been conclusive on this topic. If the number count of satellites can trace the density of the environment, we have relevant studies both supporting the presence of significant overdensity in this number count, and also the scenario where AGN hosts are surrounded by a, let's say, regular galactic population. And in this context, feedback from AGN is debated as a further complicating factor. Since AGN outflows would be able to affect the satellite population, both enhancing or quenching their star formation activity, in this way affecting our capability to detect them. So maybe AGN feedback can be blamed for this inconsistency in observations. And here is my contribution. That is, what can be the influence of bright quasars onto their companion galaxies at redshift larger than 6? And I did this through the help of a suite of cosmological simulation. For my analysis, in particular, I took advantage of the Bareilles simulation suite. I mainly focus on two zoom-in cosmological and hydrodynamical simulation of the suite, where the same initial conditions evolve in a massive halo of about 4 times 10 to the 12 solar masses at redshift 6. And whereas in the first simulation of these two, massive black holes accrete and eject powerful outflows in a big cone, in the other one, only star formation and supernova feedback are implemented, and I used it as a control run. This is the gas surface density of the run with the biconical feedback at different redshift, where you can see the evolution of the overdensities. And here you can see a short summary of the simulation parameters. So let's jump to the difference of the properties of the satellite galaxy. The median properties that you are seeing here of the satellite do not show significant differences, as the variation are well within the error bars. We have here the gas mass, the star formation rate, the stellar mass, and the metal fraction for no AGN, the simulation, the control run in blue, and in red, the simulation with the feedback, the AGN feedback. So the effect is very small, especially after only a giga-year of evolution. But in particular, in the median, we cannot disentangle those galaxies really affected by an AGN outflow from the others. And this is because the outflow are not isotropically ejected. For this reason, I built a toy model in order to identify the real effect of the AGN network, considering the different duty cycles, the different accretion rates, and the different emission axes. And from only momentum conservation assumptions, I define the integrated flux as the total energy emitted by a single AGN and received by a certain target galaxy. Here you can see a schematic representation of how the model works. Here you have the AGN, and this is the target galaxy with the gas content within the two objects. And eventually, if we sum the contribution for all the active black holes in the simulation, we get an estimate of the total energy absorbed by a satellite. I show you a typical case. This is the velocity map of the gas in the neighborhood of an active black hole, and these are its two biconical outflows. Each point on the map marks the position of a satellite, and in particular, this colored dot represents a subsample of satellite I selected to refine the comparison. These are the satellites that I matched between the two runs. And this is the final comparison. Again, no AGN is in blue, and the biconical feedback simulation is in red for the galaxy couples I've just shown to you. And this is the evolution of the cumulative integrated flux for each galaxy's cosmological history. That is the total energy absorbed by each galaxy from all the AGNs in the run. And here you can see how the stellar mass of each couple evolves, and also its relative difference, and also the star formation rate along with the relative difference. And as you can notice, each galaxy shows a higher star formation rate and stellar mass in the run with the AGN prescription. And this enhancement is compatible with an increase in the energy absorbed by each galaxy. Moreover, it seems that the more a galaxy is influenced, the higher is the effect of its star formation rate and total and total stellar mass. And so I can draw my conclusion. My take-home message is that even if I was not able to find a relevant effect of the AGNs on the satellite population as a whole, in the single cases, it appears that the feedback has a positive effect onto the star formation process. And the developed toy model is a useful tool which can be implemented in different cosmological simulations with different geometries and of emissions. So thanks everyone for the attention.